Okay, so the first of the two talks this afternoon will be on data structures. And the key bit will be motivating why does PyFR use the data structures that it does. As at first glance, they may seem somewhat unintuitive and more complicated than what you may be familiar with in other contemporary codes. The first thing I'd say in this regard is one of the keys to extracting good performance is choosing the right data structures. It really doesn't matter how much effort you put into optimizing your kernels or even your numerical method. If your data structures are wrong, they will very quickly impose upper bounds in terms of how much performance you can extract. Hence, this is somewhere where one needs to put a lot of care and attention to getting it right. And of course, changing data structures later can be a relatively painful process. So this is when we first designed PyFR, where I spent a lot of time thinking about what operations did we want to do where and how we should lay things out. To begin, within the context of modern hardware, which is what I spoke about earlier today, I'd like to lay out what I would say are 4 key principles that we have to keep in mind when picking data structures, especially for GPU-accelerated codes. The first point is one which someone raised in the Q&A earlier, and that is the fact that on GPUs, host-to-device data transfers are expensive. The solution there is that all kernels must therefore be offloaded onto the GPU, as this avoids the need to routinely move around large chunks of data. The only time data should ever be moved from GPU is when that data is being sent to another rank in a multi-GPU simulation. These are so-called halo exchanges, or where we actually need to inspect the solution itself, say to write it to disk or to do some post-processing. But during the course of a time step, there should never be any routine need to shuffle data around. And incidentally, this is one of the reasons why it's so hard to meaningfully GPU accelerate legacy codes, as you really only begin to see the benefit of the GPU once perhaps 90% of your kernels are offloaded. Before then, any benefit you get from the GPU will typically be more than offset by the cost of moving data around. The second point to note is that memory allocation as an operation is expensive. Allocating and deallocating memory takes a relatively long time. This is especially true on GPUs. In addition, frequently allocating and deallocating memory can give rise to something called memory fragmentation, which is again bad and can lead to out-of-memory errors if it gets out of hand. Hence, for HPC code, it's very important to allocate all memory upfront, with no allocations taking place during what I'm calling the critical path. But broadly speaking, that means no allocations during a time step. Next, and this is something that I hopefully motivated in my previous talk, is that memory bandwidth is a scarce resource, and thus we should design our kernels in a way that minimizes how much data they need to move about, as in how much memory they read and how much memory they write. Even if that means expending flops to recompute certain quantities on the fly, that's still usually a worthwhile trade-off compared to pre-computing something and reading it in. As again, flops these days are relatively inexpensive, and we're getting a lot of them thanks to Moore's law, but memory bandwidth isn't going anywhere. And this even comes back to when we're thinking about designing parts of the algorithm. It's how can you come up with an algorithm that's amenable to allowing you to recompute as much as possible on the fly rather than requiring expensive pre-computation. The fourth point is that not only is memory bandwidth a scarce resource, but to achieve a meaningful fraction of peak memory bandwidth, your memory accesses have to be coalesced, as in the amount of bandwidth you will achieve if you're just reading and writing 4 bytes of data is dramatically less than if you're reading and writing data in, say, 128-byte chunks. And thus, we need to be considerate as to how our kernel will access memory, the order in which it will access memory. What's particularly insidious here is any kind of memory indirection. Indirect accesses are somewhat pathological in these kind of codes and are a prime reason that can prevent you from getting a good fraction of memory bandwidth. And thus, we need to arrange our data to, wherever possible, allow for coalesced memory accesses and keep to a minimum the amount of memory indirection that we have to perform. So these are the 4 kind of guiding principles that have very much dictated how we do things in PyFR. Now, with that, let's go on to discuss ways in which we can arrange data with a relatively simplified toy example, but hopefully it will illustrate the point of the different kind of layouts we have. So, data layouts. At the highest level, when you're writing or designing a code, there are 3 main ways to arrange your data. These are what computer scientists like to refer to as AOS, SOA, and AOSOA. Don't worry, I'll explain exactly what they are in a second. So the AOS layout stands for Array of Structures. The idea being that, let's say we're in 1D and we're solving Euler's equation. At each point in space, we need to store a density, a momenta, and an energy. That's 3 points of data. And let's assume in our simulation we have n LE's pieces of data. The AOS layout would roughly arrange it as follows. We'd have a structure. That structure contains 3 floating point numbers, and then you have an array of those structures. And the length of that array is however many elements you have in your domain. Now, pay attention to the color coding I've given each of those 3 variables. What this effectively means is that in memory, which is fundamentally a linear 1D entity, data is roughly arranged as shown in the diagram above. Now, the nice thing about this design is that all of the data related to an element is close by. So if you have the density, you jump 4 bytes along, and you get to the momenta. You jump another 4 bytes, and you get to the energy, 8 bytes if you're using a double. This is good in terms of cache use, as it keeps all data related to an element together. So very good when we're doing indirect access, and effectively, if you want to sweep through your elements, you only have to sweep through what appears to the CPU to be a single array. So that's what a computer scientist would say is TLB friendly. Don't worry if you don't know what a TLB is. I wish I didn't have to know what one was, and I wish it didn't exist. But the downside to this particular data structure is it's difficult to vectorize. So if we want to perform a lot of operations inside of a core at once, we need to use vector instructions. So we want to operate on a bunch of elements all at the same time. The problem here with this AOS layout is that the gap between sequential densities, in this case, is 3. So the densities are not adjacent to one another in memory, they're some stride apart. And this makes this approach very difficult to vectorize. And if we can't vectorize, we can't take advantage of this SIMD, single instruction multiple data technique, and thus it's very difficult to get good memory bandwidth. This is why the AOS structure isn't typically used in high performance codes. And again, if you try and implement it on a GPU, you'll have a similar problem in that your memory accesses won't be coalesced, as all of your threads go and read some densities, except instead of reading a linear chunk of memory, each thread is 3 elements away from every other thread. So you don't get that coveted coalesced memory access, and hence it doesn't work well on GPUs either. So one of the alternatives to this is to kind of transpose things, and that gives you the SOA layout, or structure of arrays. Here, the idea is we have a structure, and each element in the structure is an array, and the length of that array is however many elements you have. So here, we have a structure. It has 3 arrays as its elements, and they are row, row U, and E. And each of these arrays is of length NLEs. So we go off and look at how this is arranged in memory, and things look a little better in some regards, in the densities for elements are now all packed next to one another, the momenta are all packed next to one another, and energies are all packed next to one another. This means that the SOA layout is trivial to vectorize. As you get coalesced access, all the threads want to access a density for a different element at the same time. All those densities are next to each other. Coalesced access, absolutely fantastic. And similarly on CPUs, you can use very large vector load and vector write instructions to, again, achieve good performance through coalesced memory accesses. But there is a problem with this design, and that's in cases where you have to do some indirect access. Since data related to a single element is a long distance away, one indirect access for an element turns into 3 distinct indirect accesses. One to get the density, another to get the momenta, and another to get the energy. And you can imagine this gets worse in higher dimensions. So indirect accesses which are already slow become even slower because you've got to do several times more of them. In addition, when you're walking through this data, so iterating through this array, it appears to the CPU as 3 separate data structures, or 3 separate pieces of data. And this can put pressure on the hardware prefetchers, because it looks like you're accessing 3 separate arrays as you're getting your density, momenta, and energies, which again can make it difficult to get peak performance. The solution to this is to move to a hybrid scheme, which is the AOSOA scheme, which is parameterized by a constant K. And in this presentation, to simplify how things look, I'm going to take K, which is a predefined constant, to be 2. But in practice, it's generally quite a bit larger. So here we have an array of structures, and the elements of each structure are themselves arrays. Except here, those arrays are of the fixed size K. And if you look at the bottom, you can see the total number of structures we need is n LEs divided by k to get everything to work out, rounding up, of course. What this looks like in memory, in the case of k equals 2, is roughly as follows. Now, the good news here is that so long as k is a multiple of the CPU's vector length, or the number of threads we're going to be operating with on a GPU, then we still get coalesced memory access, which is what we need. But since k is still, in the grand scheme of things, relatively small, the approach is still cache friendly, as a memento is not too far away from the density, which itself is not too far away from the energy. It's a fixed jump k, which k not being huge means that if you do an indirect access to get, say, the memento, there's a good chance at the same time you'll bring in the density and the energy for free at the same time. So it's a hybrid solution, and as long as you get k correct, which isn't usually too hard to determine, you're typically in a very good place. The bad news is that figuring out the indexing arithmetic, so where things are in memory, is a royal pain. And so it comes at the cost of very messy indexing if you're writing code by hand. And if you try and figure out where you actually need to go in memory to find, say, the memento for the 23rd element, well, you've got to divide by k and then take the remainder by k and add, divide, and it's not difficult, but it's a mess. And this is one of the reasons why this particular data layout hasn't been adopted by most codes. But the good news is for PyFR that we have a domain-specific language, and it can handle and take care of all of this messy indexing. Thus, this is the data layout that's used internally by PyFR, as it gives us the best of all worlds in a regime where you have to have some indirect memory access because you're operating on an unstructured grid, but you want, wherever possible, to get coalesced memory access. With that said, let's now look about how we actually apply this AOS array structure in practice. And this is done in PyFR through a form of matrix structure, is our core building block if you look at the PyFR source code. So if you recall, in PyFR, we have a set of elements, with each element containing some number of solution points. And at each solution point, we've got some pieces of data, density, memento, energies, etc. So we have our mesh, which is on top of our flow field, and then we take a look at individual elements, and then for that element, which is all nicely transformed, we've got our solution points, some number of them, and at each solution point, we need to store some data. So in PyFR, the most natural structure for this is a matrix, where the idea is that the number of rows for this matrix is the number of solution points, and the number of columns in this matrix is, roughly speaking, the overall number of elements we have in our simulation multiplied by the number of field variables. So that's, in effect, the number of things we need to store at each solution point. In this particular example that I plotted out, we have a total of 6 solution points inside each element. We have a total of 6 elements, and at each element we have 3 things. And in the AOSOA parlance, the K factor is 2. So this is a description of how something like the solution for a given element type would be laid out in memory for PyFR, with the final note being that this matrix is a row major entity. So memory goes left to right, top to bottom, is how it's actually all packed together. This is fundamentally how something like the solution in PyFR is represented in memory and how it's exposed to kernels. Now, in the case where we have a mixed grid, we typically go for one matrix per element type. So if we had a simulation with 3 element types, we'd have one matrix to store the solution inside the hexahedra, another for the prisms, and another for the tetrahedra, where, of course, the number of rows is fixed based off of the type of the element and the polynomial order you're running at, and the number of columns depends on how many elements of that type we have in our simulation. Now, sometimes we have to store slightly more elaborate quantities, such as the flux or solution gradient. And what we do here is introduce a 4th pseudo-axis into our matrix. So effectively, we tack on a bunch of extra rows. And so the number of rows is NUPTS, or UPTS. In this case, it's the number of solution points multiplied by the number of dimensions we have. In this particular case here, I've shown NDIMS equal to 2. So you can effectively think of this as being 2 matrices stacked end on end, which we'd use for storing, say, a 2D flux or 2D gradients. And there's a deliberate reason for packing it this way rather than packing it horizontally, and it all comes back to wanting to be able to cast operations as matrix multiplies and how that constrains how data must be laid out for a matrix multiplication operator to interact with the relevant quantities in the right place. So it can end up in some cases that you've got this quasi 4-dimensional matrix. But for, of course, for matrix multiplication purposes, it is just treated as a matrix, and the matrix multiplication routine is completely ignorant of the internal substructure. The second major data type in PyFR is called a view. Now, in FR, because we want to operate on unstructured grids, some operations are inherently indirect in nature. Case in point, I've got an unstructured grid here. So if you're an element, there's no easy way to figure out who your neighbor is. It's not as if you can just add 1 to a certain index as you could on a structured grid. It's fundamentally an operation that involves a degree of indirection. And that's fundamentally the price you pay for operating on unstructured grids. And we need a way of expressing this to do things such as interface calculations. So if you look here, I've got a pair of elements, and we need to be able to do something at the interface between these elements. So we've got data, what are called flux points, and we need a way of expressing that we need to do a Riemann solve between these pairs of flux points and knowing where the Riemann solver needs to look to find the relevant data. So it needs to be told on the left-hand side that the data for this element is stored somewhere, and the data for this other element is stored somewhere else, and it's possible that the element types on the left and right-hand side may differ. In PyFR, this is handled through a data structure which we call a view. And at its most fundamental level, you can conceptually think of a view as a matrix of pointers, and they point to entries in other matrices. Now, the actual implementation is a little bit smarter. It doesn't actually use pointers, and there's some extra functionality so that it can encode things such as the AOS SOA data, and also, in the case where you're pointing to something like gradient, that it knows how far you need to jump down in terms of what NUPTS is, etc. But at the most fundamental level, a view has the equivalent functionality of a matrix of pointers. And it's through this that we do our indirection. and that's how things like Riemann solves take place. They're not directly operating on the data itself, but they're operating on it indirectly through these views, which serves as lookup tables, telling the Riemann solver where to find data such as the solution for the left-hand side element and the solution for the right-hand side element stroke flux point. The third and final major data structure I'm going to talk about is something called a matrix bank. One of the, I'm not going to say quirks, but one of the design decisions we made in PyFR is all kernel arguments, so the parameters you pass to a PyFR kernel, must be specified at the point where you create the kernel. So not only is the source code for the kernel generated dynamically, but you must also specify all of the parameters to that kernel, so the arrays, the matrices, etc., at the point where the source code is generated. Now, there are several good reasons for this. The first one being we can do a lot of error checking and validation to make sure that you've passed sensible parameters, but it also allows us to make intelligent decisions as to how best to generate the source code for that kernel, as sometimes certain algorithms work better on small data versus large amounts of data. And so if we know all of that, we can make more intelligent choices about how we generate and manage the kernel. But the downside for that is when creating a kernel, it's generally necessary to specify exactly what piece of data it will be operating on. And then when you call the kernel, you effectively invoke it with no arguments, and it just does one thing, which is whatever it was told to do at the point where you instantiated it. Now, this is usually fine, but sometimes this is an unwieldy constraint. And so the way that we relax this constraint under certain circumstances in PyFR is through something called a matrix bank. And a matrix bank is effectively a collection of equivalently sized matrices, and at any one instant in time, the bank can impersonate or pretend to be any one of these matrices. And thus, to give you an example, you can create a bank that points to 4 individual matrices I've labeled here A, B, and C. You can pass that bank to your kernel, and that kernel will be designed to operate on that particular matrix bank. And then at runtime, you can make the bank behave like it is the purple matrix. So when you call the kernel, it operates on matrix A, but then can later switch to matrix C, or later switch to matrix B, as you like, without needing to recreate or otherwise change the kernel. And we remark here that it's possible for a single matrix to belong to multiple matrix banks. And this is useful for common operations, such as if you want to do the operation C equals A plus B. Without something like matrix banks, you'd need to instantiate a distinct kernel for every possible permutation and combination of matrices that you might want to add together. Whereas with matrix banks, you only need one kernel and 3 matrix banks, and those banks can then point to any matrix that you want to do this operation on, and with that, everything works out. So they are fundamentally the 3 main data types and data structures that we have in PyFR.